Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. If you recall, the last lecture we ended on this note that we have done all this analysis of different types of errors given that a closed loop system is excited by these three different types of inputs. One is a step, the second is a ramp, and the third a parabolic sort of input. So these are our test signals. But the fundamental question that still remained was whether the system was at all stable in closed loop in the first place, right? And we couldn't satisfactorily answer that question because simply we were not endowed with the tools that are required in order to ascertain that condition. Now in today's lecture and maybe in the subsequent few lectures thereafter, we shall exactly look at the first such tool that enables us to ascertain if a given transfer function whose poles are given by, the poles are given by the solutions of a certain polynomial equation, right? Whether those poles lie in the left half plane or the right half plane or on the imaginary axis. So remember, just to recall, stability dictates that all of the poles must be on the left half plane, left half of the complex plane, not just the left half, but rather we desire that the poles, so the stability notion that we now introduce is one of Bibo stability. Bibo stability. So Bibo stability means bounded input, bounded output stable, alright. So for Bibo stability we desire that all poles of the system must lie in the open left half of the complex plane. So let me explain that term open. Essentially it means that you are excluding the boundary. So if this is your real axis, this is your imaginary axis, the open left half plane would imply everything to the left of the imaginary axis excluding the imaginary axis. So why are we excluding the imaginary axis? Because remember earlier the notion of stability we discussed told us that you could still have poles of multiplicity 1 on the imaginary axis and you would still call them stable. But remember there we were talking about stability with respect to non-zero initial conditions, that is zero input response of the system. But now suppose you have a pair of poles on the imaginary axis like so, alright, and suppose you excite this system, right. So let's say the transfer function is something like s squared plus 4, alright, and now suppose you excite this system. So this is suppose your GS, and now you excite this system. So your input is also, let's say 2 by s squared plus 4, which is basically a cosinusoid of the same frequency. Then when you take the overall inverse Laplace of this, you will find that Ys is nothing but GS into US, alright, and therefore Yt will be the Laplace inverse of this GS times US, alright. So remember now we are concerned with the stability with respect to the input, alright, not just with respect to the non-zero initial conditions of the system, alright, and therefore if you allow such an input, which is of course bounded in the sense that it does not blow up, so there are different notions of boundedness. So of course a cosinusoid or a sinusoid, its amplitude is held constant, right. So, it never goes to infinity in that sense, right. Its magnitude never, amplitude never goes to infinity, it does not blow up, it has got a constant envelope. So, given that that is the situation, that it has got a constant envelope, right, then what can we say about this? What we can then say about this is that given that you excite a system with this sort of an input, and suppose your system's original poles are on the imaginary axis at exactly the same place where the modes of this system appear, then the overall Laplace inverse would be tantamount to finding out that of s squared plus 4 whole squared, right. And this we know is problematic, because the moment we expand this, right, we are going to have terms like, of course, sine 2t, but we will also have terms like t sine 2t, or like cos 2t and t cos 2t, terms like these. Now, of course, these terms are not problematic, because if you excite something by a sinusoid, you expect to get a sinusoid at the output. But now, notice that because the system's pole, all right, and the pole due to the input happen to coincide, all right, you have these terms arising, all right, and that is a problem. So, therefore, when we are talking about stability with respect to bounded inputs, we also exclude even single poles or poles with multiplicity unity on the imaginary axis, and we say we exclude the imaginary axis entirely. Okay. So, then it stands to reason that the question of stability is one of this: ascertain if all the poles of the system are in the open left half of complex plane. Okay. So, this is the first step. If so, then system is stable in this Bibo sense. Okay. If not, and we frankly do not care if the poles are on the imaginary axis or on the open right half plane, but if not, then we uncritically call the system as unstable. Now, this is all very nice and fine at the conceptual level, but the question still remains. Suppose I give you a polynomial such as a0 plus a1s plus a2s squared plus so on till a n s to the n, an nth degree polynomial. Short of finding the actual roots of this, so short of solving for Ps is equal to 0, how do we address the stability question? And remember, if I haven't mentioned in my earlier lecture, just let me mention this at this point, that you might think, okay, the quadratic can be solved in a closed form, but that does not work for polynomials beyond the, for general polynomials. Of course, for some special structure of polynomials, you might still be able to solve for the polynomial. So, you do not come up with a pathological case and say, oh, here is a 16th degree polynomial that I have been able to ascertain the roots in closed form. Okay, there might be some special structure, some terms might be missing which allow you to solve for such polynomials. But in general, for a given polynomial of degree more than 4, so for quadratic we obviously know the formula, Sridharacharya's formula. For cubic there is Cardano's method. For fourth degree polynomial there is this method called Ferrari's method, okay, which gives you the formula. Of course, it is a very cumbersome sort of a formula and you would probably not like to remember such formulae. It is not as easy to remember as that of the quadratic equation. Okay, so the roots can be expressed in a closed form as functions of these coefficients, but it is not easy to remember them. But beyond fourth degree polynomials, the case is just hopeless. Okay. So, solving for this Ps is equal to 0, of course, these days you have computers and you might think, oh, I will just feed it to the computer. But remember, the computer also does it in using some numerical techniques. So, those days when these questions of stability arose, people wanted to find a tool, and we shall see later on that even now, even if we can solve for these roots, there are still uses of the techniques that we will develop for ascertaining the stability without solving for the actual locations of the roots. Okay. So the question remains, can we bypass this, solving this PS is equal to 0, and yet ascertain if all my poles are on the open left half of the complex plane? Turns out we can actually do more, but for now, for starters, we will just focus on answering this basic question, and this is given by this Routh-Hurwitz criteria. Let me warn you at the very outset that of all the topics that we will cover in this course, if you go through standard textbooks on these topics such as Routh-Hurwitz criteria, root locus, Bode plots, Nyquist criteria, so on and so forth, excluding this Routh-Hurwitz criteria that we are now going to cover, every other topic is covered in pretty much great detail. So even if it may not be very mathematically rigorous to a mathematician's liking, at least at the undergraduate level, you will be able to grasp conceptually why those conditions are true, right? So when you're plotting root locus, say for example, later on in this course, you will see that there are certain rules. Of course, the rules are not the same as the root locus itself. Root locus has a definition of its own. But you see those rules you don't have to really remember, unlike most people who might tell you that you might have to remember those rules. No, most of it follows from very basic concepts, ideas of complex numbers itself, right? Similarly, when you draw these Bode plots or you draw this Nyquist criteria, it will be based on something called the principle of arguments, right? But it turns out that for this Routh-Hurwitz criteria, you'll go through all standard textbooks at the undergraduate level, and what you'll find there is, it's as if people are just invoking this, that this is how it happens. And there's hardly any room for asking the question that why is it true? Why does it happen? Why am I simply going to draw up this so-called Routh table and just going to look at certain terms, look at the sign changes and so on and so forth, and why is that going to tell me the answer, right? So of course, if I just want to mechanically elaborate this process of drawing up this Routh-Hurwitz criteria, I can actually take up an example of a polynomial and show it to you, and you'll remember it. And you can use it mechanically for the rest of your lives without even bothering about why this criteria works. And it turns out that these undergraduate texts are not to be put at fault, because you see this Routh-Hurwitz criteria, the original derivation involved some very sophisticated mathematics. It used some Sturm series, okay, which is hardly within the purview of undergraduate engineering curriculum. So that's the reason why this, although it's a very useful result, so the textbooks could not possibly do away with Routh-Hurwitz criteria as a topic at the undergraduate level, but a detailed derivation or an insight into this is, or at least used to be, truly well beyond the purview of an undergraduate curriculum. But it turns out that not very recently, and that is to say maybe some 30 years or so, maybe some 25 years back, there was this work by a group of researchers who made it accessible to undergrad students. Okay, so now you no longer have to resort to this original derivation of the Routh-Hurwitz criteria by Routh, who incidentally was a very famous, celebrated mathematician, contemporary of Maxwell, right? He won the Adams Prize, actually, if I'm not mistaken, for actually promulgating this particular criteria. Okay, so nonetheless, the point being that this 25 years back, this insight behind this result was made pretty lucid, and I believe pretty accessible even at the undergrad level. So in this lecture, I'm going to just try and do that. So I'm not going to give you an exact rigorous proof, because that will be tantamount to going through a complete research paper in all its nitty-gritties. If you want to look for this result here, let me give you the title of the paper. So this is a paper that came out in the IEEE Transactions on Automatic Control. Okay, so it's basically in volume 3, volume 43, number 3, and it's a paper that came out in 1998. So number suggests it's in March 1998, and the title of the paper is An Elementary Derivation of the Routh Hurwitz criteria. Now, although it says an elementary derivation, I believe that certain groundwork needs to be done before you are actually in a position to appreciate this. So, what I shall attempt, let me set out my goal first in this lecture and maybe the next few lectures. My goal would be to sort of equip you with certain tools and some insights into why the results in this paper, which is just basically a 4 or 5 page long paper. So, it might seem like it is very easy to read, but then you need certain understanding in order to be able to appreciate the results of this paper, and that is going to be my goal. I am going to give you some glimpse into the tools that are going to be used in proving this result in this paper. I am not going to prove this result as it stands in this paper. For that, you have to download this paper and read it up, okay, if you are interested. But I am going to sort of hopefully convince you and present pretty convincing arguments or reasoning, at least hope to present more convincing arguments than those given in your standard textbooks, and hopefully you will be able to appreciate the beauty of this particular result. Okay. Okay. So, enough tall claims made, let me just go about the business now, right. So, let us start with let us say an arbitrary polynomial. Suppose you have Ps, which is given by a0 plus a1s plus a2s squared plus dot 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 till a to the n s to the n. Okay. So, we can always factorize this in the product form, where we pull out this highest coefficient, right, and then we can write this as s minus pi, maybe to the power ti, all right, where ti is what? The multiplicity. Multiplicity of pi, right. So, this is one form of writing this, okay, and I could be from 1 through m, okay. So, basically you will then have the condition that T1 plus T2 plus dot 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 till Tm is equal to n. Why? Because it is an nth degree polynomial. So, over the complex field, right, even if these coefficients are real, so ai, these are real. So, even if these coefficients are real, the roots of this polynomial can be complex numbers. So, if you admit such factorization, and of course here pi is a complex number. So, if you admit such factorization over the complex over the field of complex numbers, then you can write it in this form, and of course then the total number of zeros or the total number of roots of this polynomial must be equal to n. That is a fundamental theorem of algebra. So, the total number of roots are n. Now, if you count every root, every distinct root, okay, so pi is not equal to pj for I not equal to j. So, basically these are all distinct roots, that is why we are counting these multiplicities together. So, suppose it is s minus 4 into s minus 5 into s minus 6 whole squared, then even though it is a 4th degree polynomial, yeah, for 4 the multiplicity is 1, for 5 the multiplicity is 1, for 6 the multiplicity is 2. So, if you call P1 as 4, P2 as 5 and P3 as 6, then T1 is equal to 1, T2 is equal to 1 and T3 is equal to 2, and T1 plus T2 plus T3 is 1 plus 1 plus 2 is equal to 4, which is the degree of the polynomial. So, hopefully that kind of illustrates what this expression basically means. Okay, so, this is T, it might look like epsilon, but it is T. Okay. So, we can factorize it in this fashion. Now, notice, let us cast our attention back to the question we are trying to answer. What is it? Whether the poles of the system are in the open left half of the complex plane. So, let us ask ourselves the question, what if the poles, or rather the roots of, what if the roots of PS are in the open left half of complex plane? What can we deduce? And here is the profound observation, all right. So, draw this complex plane like so. Let us say this is the real line, this is the imaginary axis, right. Now, you can have complex poles which are real, or complex roots rather which are real, or they could appear in complex conjugates. Remember, if the coefficients are real, then complex poles must appear as conjugates. Okay, that is also another result that by now you must be familiar with. So suppose there are, okay, let me not use different colors at this point. Suppose there are poles like these, okay, arbitrary. But the only common thing about this, only thing about this distribution, we are not bothered about the exact location, whether this is -4 plus j6 or this is -2 plus j2. We don't care about the actual magnitudes of the real and the imaginary parts of these poles. All that we are bothered with is that these are on the left half plane. So what is it? What is the common thread that connects to all of them? Notice, as you take this, this is the j omega axis, right? So suppose you keep taking discrete points on this j omega axis. Consider any pole. So consider any, why am I again calling it pole? It's a bad habit. Now I am concerned with a polynomial, so I should say root. Any root of PS on open left half plane. So that's how I'm going to now denote this, OLHP in short, right? So suppose it is real. Now look at this phasor, okay? So this is j omega 1, this is j omega 2, this is j omega 3, so on till it goes to infinity, right? So what I am saying is, look at the phasors j omega 1, so let me name this pole as P1, j omega 1 minus P1, j omega 2 minus P1, j omega 3 minus P1, so on, yeah, where omega 3 is greater than omega 2 is greater than omega 1, so on, right? Okay, what do we observe? The observation is that if you look at the argument or the angle, okay, you see that angle of j omega, okay, not j omega k minus P1, yeah, is greater than the angle of j omega L minus P1 if L is greater than, or rather let me say omega k is greater than omega L. Why am I saying this? Look, what is the angle? The angle is, this is, let us say phi 1. Now you look at this here, this is phi 2, right? So if you go up, higher and higher you go in this direction, as you proceed along this imaginary axis, as you keep increasing the magnitudes of this omega. So omega is like your running variable, you are choosing discrete values of omega, omega 1, omega 2, omega 3, so on and so forth. As you go along this, you see what happens to this phasor is, of course, we are not concerned about the magnitude of this phasor. The magnitude of this phasor also increases, but we are not bothered with that. We are focusing on the argument of this phasor. And what we notice is that as you go up, if your pole P1 happens to be on the left half plane, it keeps increasing. So this we can summarize as saying that this phase of, sorry, I have put this bracket in this wrong place here. Yeah. So this phase of j omega minus P1 increases monotonically with omega. If you observe this, you have understood almost half of what our argument is going to be based on. So every now and then we are going to invoke this property, okay. It turns out that this is not just a necessary condition. So here what I have demonstrated to you is that if, so let me summarize that. If PS happens to be a polynomial, all of whose poles or roots are on the LHP, open LHP, then for every pole, this function, this phasor, monotonically increases with omega, okay. But it turns out that that is not just a necessary condition for the roots of the polynomial to be on the open left half plane, it is also a sufficient condition. In other words, if you start with this condition that every pole, for every pole of a system, I don't initially know if the poles are on the left half or the right half or the imaginary axis, but if I am told that for every pole of a particular polynomial, this particular function, that as I go up from omega is equal to 0 to omega tending to infinity along the positive imaginary axis, yeah, then this function, this argument increases for every pole, okay, then I can immediately deduce that this polynomial's poles must all be on the open left half plane. So it is a necessary and sufficient condition. Not just this, there is something very interesting also happening here. Notice that for every such pole, for every real pole pi, the function j omega minus pi, real pole pi such that pi is negative, or rather, yeah, in this case, yeah, pi is negative. So this is the pole, yeah. So for every pole such that it is on the left half plane, open left half plane, yeah, this is equal to 0 at omega is equal to 0 and tends to pi by 2 as omega tends to infinity. So therefore, if I am using this notation, the delta theta, the sum total of the theta as omega goes from 0 to infinity is going to be pi by 2, okay. So this is the theta for pi, okay. So let me make that notation a little cleaner. So let me put this omega is equal to 0 and infinity to the delta, okay. So corresponding to this pi, this is the function, okay. So this is the net change, this is the net change in j omega minus pi for omega going from 0 to positive infinity, yeah. So I notice that if my pole pi is on the left half plane, then the total change in phase as omega varies from 0 to infinity, if I map this, it is pi by 2, okay. Now of course this is for real pole. Now I have not yet shown what happens for complex. What happens for complex? You might argue that look, for the complex pole, if I consider this pole individually, yeah, at omega is equal to 0, this is some minus alpha, yeah, and at omega tending to, so at omega is equal to 0 for a complex pole on open left half plane, the angle j omega minus, so say the pole is pk, yeah. So then this is equal to minus alpha, or maybe alpha looks very close to infinity, so I don't want to confuse that. Let us call this minus beta, okay. So this is minus beta, and as omega tends to infinity, this angle, the same angle j omega minus pk, this tends to pi by 2. So therefore, for this particular pole, now you might say, okay, for real pole I understand that it goes from 0 to pi by 2, hence the net change is this pi by 2, okay. But for a complex pole, see this change as omega goes from 0 to infinity, this theta for pk, I hope that is the notation, yeah, that is the notation. So this is nothing but pi by 2 minus beta, beta k, let us say, so let me call that beta k, yeah, this is going to be pi by 2 plus beta k. So that seems like a spoil sport, no? But recall that for every such complex pole, pk star, which is the conjugate, is also a pole, And what can I say about pk star? Now look at pk star. If this is pk, then this is pk star. So for pk star, now notice, for pk star as omega is equal to 0, this angle j omega minus pk star, this turns out to be now exactly the opposite of that. So this is plus beta k. Yeah, so this is plus beta k. And as omega tends to infinity, again, it's asymptotic. So both of these, for a point that is infinitely far away on the imaginary axis, these points pk and pk star are almost coincident. Yeah, that is the fundamental thing. No, when you are very far away, when you are infinite distance away. So for example, for someone in let's say New York, right, the person living next door to you is almost basically at the same place as you, right, because the distance between your city in India and New York is so large that compared to that distance, the distance between the two houses that are adjacent is barely anything, it's 0. So by the same argument, both these pk and pk star, for both of them, as omega tends to infinity, this angle j omega minus pk star is equal to pi by 2. So therefore, for this we get that omega going from 0 to infinity, this theta pk star is equal to pi by 2 minus beta k. So therefore, if I now sum together these two, the effect of the two, because remember complex, and it's a legitimate operation because I am not cheating you, because see, the moment I have a complex pole, I have its conjugate as well. I have a complex root, sorry, I have its conjugate as a root as well. Let me just get rid of this bad habit of always calling this a pole. Root. Let me also call this. So used to calling it a pole. I'm dealing with polynomials, so it should be roots always. Henceforth, if I even misspeak and say it's a pole, please read this as root so far as this polynomial is concerned. Okay. So what I'm saying is then, therefore, that look, this pk star plus omega is equal to 0 to infinity theta pk is equal to 2 times pi by 2. So for two complex poles, it is 2 times pi by 2, and for every real pole on the left half plane, it is 1 times pi by 2, right. So therefore, the general statement is, and here is the general statement, for Ps is equal to a0 plus a1s plus so on dot dot till an s to the n, yeah, if all poles, again sorry, if all roots lie on the open left half plane, then the net change, let me go about this, the net change in theta as omega goes from 0 to infinity in P of j omega is equal to n pi by 2. Why? Now notice I am going to make use of this product form expression. Yeah, notice this. So you know that the argument of the product of two complex numbers is equal to the sum of the arguments of the individual components, right. So therefore, I am going to now make use of the fact that if this is P, this is also in turn equal to n times product, as I said, S minus, what did I call it, Pk, oh Pi, Ti, okay. So this is Pi, Pi, Ti, I going from 1 through m, right. So for every pole, whether repeated or not, so if it's repeated, you just count it Ti times, yeah, and then that makes it like m times, and some of them are repeated Ti times, right. So therefore, the net phase change, so notice that basically, for example, let's say you have s minus 2 or s plus 2, sorry, it must be s plus 4 and s square plus 2s plus 2. So for this, of course, I know where the poles are. This is nothing but s plus 2 into s plus 4 into s plus 1 whole squared plus 1. So, if I want to now write this in this form, I can write this as s plus 2, or let's make this squared. So, s plus 2 squared. So, let's say this. Now, I am not saying, by the way, note that I am not saying that you have to, every time you encounter a polynomial, you have to write it in this product form. Okay, but I am saying that this is just for an analysis purpose. Of course, if you can write it in this product form, then you can find the roots. But I am saying that irrespective of whether you are able to write it or able to see that this can be written in how this can be written in this product form, we are saying it can be written in this product form. Even if it is given in this form, there does exist a product form expression such as this. We are not interested in exact evaluation of this product form, but because it is written in this exact, it can be written in this exact product form for every component of this product form, for every individual component of this product form, I can write this as s plus 1 plus j1, s plus 1 minus j1. Okay. So, now notice, where are my poles? This is just an example, just to illustrate this point. Okay. I hope that I have kind of given you a solid proof of this. So, this is at minus 2, and because there is a repetition, let me draw another here, minus 2, then there is another one at minus 4, and then there is a pair here. So, now notice that the phasor going from here to here, the net phase changes. If this is minus beta, then it goes from pi by 2 plus beta. Okay. For this fellow here, this angle is similarly beta, and this is again pi by 2. So, this is pi by 2 minus beta. Notice that for this pole here at minus 4, this is 0. So, it goes from 0 to pi by 2. So, this is for this fellow, let me use a different color. What color should I use? So, this fellow it is pi by 2. What about for this fellow repeated? For each individual block, okay, let me use a different color. For each individual block, it is pi by 2 plus pi by 2, because this is multiplicity 2, because ti is equal to 2 for this fellow. So, let me call this my, this is my P1, this is P1 conjugate, this is P2, alright, and this is P3. So, in this case, with that sort of notation, this is T3. So, T3 is equal to 2. So, what is the net phase change? If I sum this up together, it is pi by 2 plus beta plus pi by 2 minus beta plus pi by 2, or let me use the color coding for convenience. So, now if I want to find out delta from omega is equal to 0 to infinity p of j omega, this is going to be nothing but, let me color code this, pi by 2 minus beta plus pi by 2 plus, sorry, this was plus, so this is minus pi by 2 minus beta, right, and then we have this purple colored thing. So, then there is this pi by 2 times T3, and T3 is basically nothing but 2. So, this is going to be 4 times, let me sum that up together in black. So, this is going to be nothing but 4 times pi by 2. What is 4? 4 is nothing but n, no, because Ps is a 4th degree polynomial. So, this is equal to, so in general, as I claimed here, you see here I think, So, in general this holds 4 times pi by 2, n times pi by 2. So, now what I am not going to prove, but I am going to sort of urge you, maybe it is provable, but it is just too lengthy and it will take us too far afield again, and I believe that it is not very important to know that detail of the proof. At least hopefully I have been able to present some sort of a convincing argument to you to suggest that this monotonic phase property holds. Now, what does this mean? It means that if a polynomial has to have all its roots on the left half plane, then it suffices that if I study this polynomial's phase as it goes from 0 to infinity, yeah, and if that turns out to be n pi by 2, if it is monotonically increasing and it goes to n pi by 2 from 0, then its roots must also be on the left half plane. So, I have not proved the latter part, by the way. I have shown you that if the polynomial's roots are on the left half plane, then this condition is true. But what I am not proving, but I am claiming, and it will, as I said, it will take us too far afield, that is why I am not proving this. What I am claiming is that the reverse is also true. So, this is a necessary and sufficient condition, okay. So, this condition on the phase, the monotonic increase of the phase from 0 to n pi by 2 for an nth degree polynomial in real coefficients is both a necessary and sufficient condition, okay. So, it is a necessary and sufficient condition, and we love this. Why? Because now this gives us a handle, an alternate way to check if the roots of a polynomial are in the left half plane without ascertaining where exactly those roots are. So, short of finding the exact locations of those roots, we now have some sort of a handle over this. Again, I am saying I have not proved the sufficiency, okay. I have just proved the necessity, that if the roots are on the left half, then this monotonic phase increase property from 0 to n pi by 2 must hold. The sufficiency is also true, which I am not proving, but I am claiming, I am sort of invoking on you, but hopefully this appears less of an imposition than most textbooks would do. At least now you have some sort of an intuitive understanding of why this property holds. A quick consequence of this property, again I made a silly mistake here. So, this is going to be plus pi by plus some angle theta, you see, because of this fellow sitting over here, right. So, this should also contribute, no. So, this should actually be indeed 5 pi by 2, not 4 pi by 2. This pi by 2 will come in for this. I missed counting this. This is actually not a 4th degree polynomial, it is actually a 5th degree polynomial. So, because I added this square later, I forgot about it later. So, that is why I kept counting this as a 4th degree polynomial. It is indeed a 5th degree. You see 2 plus 1 plus 2. So, that is 5, right. So, it is 5 pi by 2, which is consistent with how we understand this system, right. What is a quick consequence of this property? Now, note that P of j omega, let me take an example, because nothing works better than an example. So, let us, okay, what example should I take? Do I have an example ready here? Let me see. Yeah. So, let me take an example, say s cubed plus 10 s squared plus 31s plus 1030, okay. Maybe I just picked it up from some textbook, I do not exactly recall, okay. So, let us say you have this polynomial. Now, notice if you pass on this j omega to this, yeah, then what does it look like? It looks like j omega whole cubed plus 10 times j omega squared plus 31 times j omega plus 1030. Then what you have is 1030 minus 10 omega squared plus j omega, you take common, then you have 31 minus omega squared, yeah, because j cubed is nothing but minus j, right. So, notice that for any polynomial, this is an even part and this is also a real part, okay. If you pass on the argument j omega in place of s here, which is to say that you are basically evaluating the polynomial along the imaginary axis, which is what we have started with from the very beginning, no. We have said that we are interested in mapping this. You see, let me go back a step behind. When you had basically, when you were plotting functions of x, so this is x, this is fx, alright. So, this is your independent variable, this is your dependent variable. So, at every x you find out where does fx send x to, yeah, and you find out this is fx1, then you take x2 and you see that this function f sends x2 to fx2 here, yeah, and of course, if you do this for all points here, you get a plot something like this, okay, but this is a function of a single real variable. But now notice you have a function of a complex variable. So, basically here this independent axis was called your domain of your function, and this is basically the range of your function. But now when your variable is a complex variable, then your domain is this. Now it's no longer the single axis, no, it's a double variable, because basically you have a real part and an imaginary part in your domain, yeah. And also your range, which is this function, this range also is something like real part of P, okay, let me call it Z for the time being, or S. So S is the complex variable, real part of PS, and this is the imaginary part of PS. So obviously if you pick some random points here, unlike in the real case where in the same graph you could show how x varies and fx varies with it, here there is no way you are going to be able to plot it, no. Even if this was a single function, you could have still plotted it on a 3D plot, right. But remember, both your domain and your range are 2-dimensional, yeah, and you cannot plot something 4-dimensional on a graph. So the way we do this is generally we take some contour like this here, yeah, on our domain here, and then subject to every point here, so we call this S1, this is S2, this is S3, so on, we map it through this function. So let us say we pass it through PS, and then here we have PS1, here we have PS2, so on, yeah. And if we take these points sufficiently close enough, then we say that corresponding to this closed contour that is being mapped here, we get some other contour that is also here. Why must it be closed? Because remember, as you are coming back to S1, there is a single valued function, no. So for P, if you pass S1 through P, you get a unique point. So you started with S1 and you end at S1, so you get a closed contour here. So here also you started with PS1 and you go one way around and you come back to S1 and you evaluate PS1 again, so you also close a contour here. So contour here will lead to a contour here. So that is unfortunately the best visualization you can get, unlike this visualization of a single variable function on the real variables, yeah. This is the best possible visualization you can get. So we are doing something very similar. Instead of choosing this random or arbitrary contour, what we are saying is we are choosing a very special set here as our domain, sorry, not that J here. So what we are choosing as our domain is this, the positive imaginary axis. This is our domain from omega is equal to 0 to omega tends to infinity. So this is our Argand plane. So in this Argand plane, this red part that marked here, this is the domain, and we are sending this through this mapping PS, yeah, to this, which is nothing but real of, now it is P j omega, and this is imaginary of P j omega, which is to say that for every value of omega that you give me on this, yeah, this is omega 1, this is omega 2, so on and so forth, I will pass that value here in this function. So this is going to tell me what the x-axis projection is going to be, yeah. So this is going to be giving me my even or real part for some omega 1 or maybe omega 2 or some omega k, and this is going to tell me my imaginary part. So I take this and this is going to be my mapping, okay. So this is suppose my Pj omega k, okay. So this is, let us say, some omega k here. So what I am saying is that now look, what have I found? I have found that as omega goes from 0 to infinity, P of j omega goes monotonically, this is important, monotonically from 0 to n pi by 2, okay. So if P of j omega goes monotonically from 0 to n pi by 2, then what can I say? What I can say is that I split up P j omega into real part, P real of j omega plus j times P P imaginary of j omega. So remember that this P imaginary and P real, the way I have split it up, because I have pulled this j out. So these are now both real polynomials, no? So polynomials with real coefficients, yeah, because I pull this j out now common, okay. Notice this example here and it will be clear. I pulled out this j, so basically now this part is going to be my P imaginary and this part is obviously P real, so its coefficients are 1, 0, 3, 0, minus 10, its coefficients are 31 and minus 1, they are all real numbers, okay. So what does it mean? Now if you translate this, so look at the P j omega plane, yeah, because I do not have the luxury of looking at just the fx plot like I did for a single variable real function, no, a real function in single variable. Here I have to look at what happens to this. What does it mean in the complex plane, in the P j omega plane? So this is real of P j omega and this is imaginary of P j omega. Now if I want to find out this phase for a particular omega, what do I have to do? I have to just take this omega here, and what is the phase? The phase is nothing but this angle, no? And what is this? This angle, what should I call it? Some gamma is equal to nothing but tan inverse the imaginary part of, or rather I have already given it a name, so let me use that nomenclature. So this is nothing but P imaginary j omega upon P real j omega. Actually I can get rid of this j. This j omega I have kept here just to show that it is coming from passing this argument j, because now you see once you pass this j omega here, you have gotten rid of the j, you pulled out the j here, no. So these are purely functions of omega now, but anyway we will let it pass, it is just a fine point, yeah. So now the assertion in this previous slide that we made is that this gamma, the way we have defined this gamma must monotonically go from 0 to n pi by 2 if, okay, if you already know. So I have run out of space, so I am not going to write that, I am just going to say that verbally. So this gamma must monotonically go from 0 to n pi by 2 if PS has to be a polynomial with all its roots on the open left half plane, right. What does this monotonic increase mean in practical tangible terms? If gamma keeps increasing, as I am increasing omega, so notice this is my domain, the domain is just this part. So as I am going along this imaginary axis, going on increasing omega along this axis, I am going to find different points here. This is for omega 1, for omega 2 I am going to find another point. But what does this tell me, that if this gamma must monotonically increase from 0 to n pi by 2? It means that as omega is being picked from this imaginary axis and as omega is increasing, this must rotate counterclockwise on the on the range, yeah. So this is my domain and this is my range. So this is just like this was my domain and this was my range for the real valued function. Here for the complex valued function, this is my domain, this imaginary axis, and this is my range, and this property that gamma must necessarily increase from 0 to n pi by 2 tells me that as I increase omega, so here is the picture, sorry, so here is the picture that this is R, this is JR. As I keep picking out points from here and passing through this mapping P of j omega, yeah, in my range what I am going to see is that this function Of course, at omega is equal to 0, where does it start from? A moment's thought will tell you with this example itself. You see, this omega is equal to 0 means that the imaginary part is always going to be 0, no? Because you see, what is the lowest degree of the imaginary part? It is s, which is j omega. So at omega is equal to 0, the imaginary part is 0. So it's always going to start at this real axis. So this is where it is at, let's say, pj0. We are assuming without loss of generality that an is positive, just like here an is 1. Yeah, so we are assuming that an is greater than 0. Okay. So therefore it starts from the positive real axis, and as you keep increasing, this must go in this direction. We are not bothered about the magnitude of this, yeah. But the fact is that it must go monotonically. The phase increase means it must go in the counterclockwise direction. Till what? From 0 to n pi by 2. What is 1 pi by 2 corresponding to? 1 pi by 2 means it goes from the real axis to the imaginary axis. This is one rotation of pi by 2. What is 2 pi by 2? Another rotation of pi by 2. What is 3 pi by 2? Another rotation of pi by 2. So basically what this is telling me is that for n pi by 2, we must have pj omega traverse through n quadrants as omega goes from 0 to infinity, which means that a rough sketch, a qualitative sketch of this, a qualitative rough sketch of this variation of this pj omega, not just the angle, will look something like this. It starts from here and presumably goes through this, and maybe goes through like this. I don't care about the magnitude. So what this tells me is, look how many quadrants has this gone through? Pi by 2, 2 pi by 2, 3 pi by 2, 4 pi by 2, 5 pi by 2, 6 pi by 2, and possibly 7 pi by 2. So this potentially looks like a 7th degree polynomial with all roots on OLHP. So typically a 7th degree polynomial with all roots on the OLHP might look something like this. I am not concerned, as I said, with the magnitude. Yeah, I am just concerned with the phase. So this phase tells me that this, so it cannot be, what sort of curves are inadmissible? Some curve that goes like this. So you see that at this point, for some omega, it is this phase. And then at this point, for some other omega, so this is omega 1, this is omega 2. So omega 2 is greater than omega 1, but you see that the phase of j omega 2, the phase of pj omega 2 is less than the phase of pj omega 1. Yeah. So this is inadmissible. So the moment you have this non-monotonic curves like this, non-monotonic phase increase, such plots can only result from polynomials whose roots are definitely all not on the open left half plane. If they are all on the open left half plane, there is only this monotonic sort of a plot that's permissible. So maybe that term inadmissible needs a bit of a clarification here. When I say inadmissible, I don't mean to say that this cannot be the potential plot of any polynomial. Of course it can be the plot for any polynomial, but you have to be careful that this cannot be the plot of a polynomial all whose roots are on the left half plane, quite simply because it does not obey the phase monotonicity property, and therefore it cannot come from a polynomial all whose roots are on the strict left half plane. Another point is that this an greater than 0, you might wonder what is this, because after all at omega is equal to 0, this is a0, right? But naturally when we say that all the roots are on the left half plane, then the coefficients, all the coefficients of a polynomial must have the same sign. So we are assuming that if an is greater than 0, then a0 must also be greater than 0, otherwise there is no point in looking for, if there is a sign change in the coefficients of the polynomial, yeah, then there is no question of that polynomial having all its roots on the strict left half plane. We will talk more about this at a later stage as well. We will show you, in fact, illustrate this maybe in the next lecture or so. Okay. So we will end this lecture here today, and we will carry on with this more, we will see more of the consequences of this monotonic phase increase property and this subsequent crossing across these n quadrants, yeah, and this has very far reaching consequences which we shall see in the next lecture. Till then, take care, thank you all.